Okay.
Okay, so the second talk of this session is a talk by Francesco Gavazzo, who's going to tell us about quantitative rewriting. So you can take it away.
Okay. Thank you very much. Um, so as said, the main topic of this talk is rewriting, which I'm sure you all know what it is. But in this talk, I will just take a specific point of view on rewriting. Namely, I will look at it as a way to extract, if you like, or make explicit the computational and operational content of equality or of equational deduction. And the way I take this perspective is that this turns out to be quite useful when we study programming languages, where we can essentially specify our language or our calculus for a language by means of equations. So here is a running example in which we have a computational core, which for simplicity is just taken as a bunch of combinators. Then we have some data, arithmetic, for instance, just addition and similar things. And then we can also add other features such as computational effects. So here it's specified by means of equation for probabilistic non-determinism. And then the nice thing is that once we have this equational specification, we can just use rewriting to turn the specification into something more operational. And the way we do so is remarkably simple, because we just take equality and make that directed. So we look at equality from left to right. And using this simple idea, we can formally define what a computation is. It's just a sequence of rewriting or reduction steps, and then develop a theory and algorithms upon these definitions, so that you can prove results such as confluence, termination, and so on and so forth. Now, all of that is very well known, and it has a long and successful story in programming language theory. But the point is that all of this is about equality. And we know that equality is, of course, it is useful when it comes to reason about programming languages, but it also has some limitations. So, for instance, if we are interested in intentional behavior or information flow, differential privacy, and these sort of things, equality is kind of useless. And in fact, it turns out that to reason about this sort of behavior, you need something different, namely quantitative version of equality, which are kind of metric-like notions, if you like. And in fact, if you look up in the literature, you will find a lot of theories about quantitative equalities, and one of the most a general one is the one of quantitative equational theories and quantitative algebras, where the idea is that you pick the good old-fashioned theory of equality, and now you make equality parametric with respect to real numbers. That somehow gives you a degree of error or precision into the equality. So that, for instance, if we pick the equational theory of barycentric algebra, which is the one here on the left part of the slide, then we can just take those axioms and stipulate that these holds with distance 0, so that things are indeed at distance 0, and then add some equation that produces distances or errors between terms into the equality. And for instance, if we take this equation here, what we obtain is an equational axiomatization of the total variation distance between distributions. And of course, you can repeat this game with other distances and other theories, and so on and so forth. Now, the point is that with this definition, we find ourselves in a kind of a peculiar situation in which, on the one hand, we have the traditional Boolean world, if you like, in which we have equational theories and we have rewriting to exploit their operational content. And if we look and if we move to the quantitative case, we have these quantitative equational theories, but we don't have a notion of quantitative rewriting to exploit their computational content. Now, of course, you might guess this is pretty easy to achieve. We just take ordinary rewriting and we make reductions parametric with respect to real numbers, for instance, or to other things that you want to use to measure differences between programs. So that if we look back at our running example, we just pick reduction, index them with 0, and then add some new reductions to actually produce distances. So, for instance, in arithmetic, we may add single reduction that states that if we pick the successor of a term, we can just reduce that to the term, producing an error of 1. So that's a way to operationally produce the Euclidean distance between natural numbers. And that's kind of intuitive and seems quite appealing. So we may ask, okay, are we done? I mean, is this the end of the story? And the answer is not really, because if on the one hand, this definition seems natural and intuitive, on the one hand, reasoning about these definitions may not be so. So, for instance, to me, it was not obvious what quantitative confluence or quantity determination should be in this setting. And even more challenging is, okay, so suppose we have this definition, so how can we prove properties about them? And so that's essentially the main contribution of our work. We answer all these questions by outlining a theory of quantitative rewriting. And we study the theory both in the abstract and for some specific systems, in particular focusing on term-based systems, so systems defined on first-order terms. And we prove and refine some of the theory of classical rewriting in the quantitative setting. Now, I will tell you something more about the actual contribution of the work at the end of the talk, because we need some more technical notions for doing that. But what I would like to do instead, the remaining part of the talk, is to give you a taste of the contribution by looking at a single but non-trivial example. And the example that I choose is the following. So we pick our running examples, the one that we have somehow see up to this point of combinators, arithmetic, and probabilistic non-determinism, and we try to prove quantitative confluence for the systems for the system those obtained. And of course, to do so, we first of all have to understand what is our goal. In particular, what does it mean for systems like this one to be quantitative confluent? And once we have understood this notion, well, we first of all convince ourselves that this is indeed the case. And once we are reasonably convinced, well, we should find ways to prove that. Okay, so let us begin with quantitative confluence. And well, comes with no surprise that if you want to understand what quantitative confluence is, you don't need to look at the specific systems that we have in mind, but it's something more general. So it makes sense to approach this notion in the setting of abstract rewriting. And in that setting, I mean, if you just look up the traditional definition, you see that a rewriting system is essentially a binary relations. And therefore, to come up with something more quantitative, with a quantitative refinement of that, well, you simply just move to a kind of distance or matrix or a quantitative relation in which you replace Boolean values or the truth values with, for instance, non-negative extended reals or other numerical sets, if you like. Okay, that's easy. The interesting thing now is to understand what a computation is in these systems, what confluence, church roster, and so on and so forth. And to do so, we followed an algebraic approach, which builds upon two crucial observations. So the first one, which is due to Backhouse and collaborators, is that abstract rewriting, I mean, traditional Boolean, if you like, abstract rewriting, can be formulated inside the calculus of relations. So the calculus that dates back to Peirce, Schroeder, and then Tarski, and many others. And in fact, you see if you look here on the table that, for instance, you can define what confluence is, just giving a relational inequality where you use the operators of the relational calculus, and so it's really something algebraic and point free. And the second observation is due instead to Lovier, who noticed that these quantitative relations comes with an algebra and a calculus, which is very close to the traditional one of the calculus of relations, so that we have a converse, meet, join, and composition, and so on and so forth. So, for instance, if you look at the composition and the definition of composition of quantitative relation, well, you see that it's pretty much, I mean, it follows the same structure of the usual definition of relational composition. You just replace the existential quantifier with an infimum and the meet with a plus. But the point is that because we have all these operations, we can just take the relational definition of confluence, of computation, and many others, and simply rephrase them into the language or into the calculus of quantitative relations. Now, of course, I said that these two calculi, these two algebras are pretty close, but they're not exactly the same. So we can use this analogy to come up with definition, but then we are not sure that the definition that we obtain are indeed the same. And in fact, there are some crucial differences. So for instance, if we look at a definition of the diamond property, which is given by the formula here in the top of the slide using the quantitative relational calculus notation, well, if we unfold the definition, then we come up with this formula that in particular means that whenever we have an element x, for instance, which can be reduced to two elements, x1 and x2, then the distance between these two elements that we obtain by taking this path here must be an upper bound of the distances between their common reducts. And in particular, there may be no common reduct that give us this upper bound property, but it's something that we can achieve only in the limit, so only by looking at the infimum, which is something that we do not have when we look at, when we look at traditional rewriting. But even if there are these kind of differences, it's remarkable that by playing with algebra, although this is not trivial, but with playing with algebra, we can extend many classic results in abstract rewriting to a quantitative setting, such as the Newman's lemma or the Indre-Rosen lemma, and many others, which are relevant for our running example because, well, we can start to develop some techniques to prove, well, first of all, because now we know what quantitative confluence is, and secondly, because we can start to develop some techniques to somehow try to prove these results in a modular way. So that, for instance, by looking at, if we look at our system, we see that it is essentially based on three systems. And therefore, we can start to develop techniques that tell us, well, if you can prove quantitative confluence of all these systems separately, and if you have some additional properties, then you can obtain confluence of the whole system and these kind of things. But okay, so now we know what quantitative confluence is. So the second step is to look at this notion in the specific setting of our system. And the first things that we notice is that our system is not exactly an abstract rewriting system in a quantitative way, of course. Well, because first of all, I mean, its elements are not just abstract elements, but they are first-order terms built over a signature. In our case, the signature has combinators, the application symbols, and a bunch of other operators. But most importantly, because the rewriting distance is syntax directed. And by that I mean that we start with a ground ternary relation on terms and numbers, which is, for instance, well, this is really the way in which we define distances, so the one that we have seen so far. And then what one does, although we have not seen yet, but we will do that in a moment, it extends this ground relation to more complex expressions, which essentially means that one specify how one can perform this quantitative reduction inside using the ground relation, but inside other terms. And that essentially amounts in the quantitative setting to explain how the distances produced by the ground relation propagate along function symbols and along other expressions. And once we have that, well, we can canonically extract an abstract system simply by taking the infimum of the reduction, of the quantitative reductions. Now, as I said, we have not really looked into point 2 so far. We have just content ourselves with showing what is point 1, and we assume point 3, but we have not seen anything about point 2. And the reason is that because this point turns out to be quite delicate. And in fact, if we proceed naively, for instance, and just mimic what happens in traditional rewriting, then we may say, well, distances are not propagated, which essentially means that if I have a ground reduction from T to S with distance epsilon or with error epsilon, and I perform the same reduction inside a bigger term, well, then the distance, the error remain the same. But the problem with that is that if we pick that definition, then we lose confluence. I mean, a lot of the time we lose confluence. And that is not just an issue of examples. I mean, we really lose, we have counterexample to important proof techniques such as orthogonality, critical pairs, and other things that you find in the rewriting literature. Well, with this definition, the quantitative setting, they simply do not hold. And in fact, if we look at our running example, we see that with this definition, there is no way in which we can prove confluence. And the counterexample is rather easy. So we pick this combinator here, which essentially is adding the successor of 0 to itself. And there are two reductions that we can perform. So the left one is really an error-producing reduction in which we pick the successor of 0 and we transform that into 0, producing an error of 1. And instead, on the right part of this diagram, we just unfold the definition so that we really need to add the successor of 0 to itself. And then what happens is that, well, that at the end of the day, I mean, these two terms have to converge to 0. But whereas the left-hand side one do that by producing no further distance, so it does so with error 0, the second one has to transform the successor of 0 into 0 twice. And each time produces an error of 1, but doing so twice, we get a distance of 2 at the end of the day, so that we see that we cannot have quantitative confluence in that case. And of course, I mean, this example shows pretty, in a pretty clear way that problems come from the fact that the combinator W is duplicated a term. And by doing so, it also duplicates the error that a reduction produces when reducing that term. And therefore, we ask ourselves whether this is indeed the source of all the problems. Namely that if this idea of duplicating is exactly what causes confluence and confluence theorems to fail. And that is indeed the case, because if we restrict our analysis to linear systems, which means that we do not allow reductions to duplicate variables, essentially, then we indeed recover confluence, we need to obtain confluence of our systems. And we do so in a really nice way, because we recover all the proof techniques that we have in the traditional setting in this quantitative and linear setting. And using those techniques, well, as I said, we prove confluence of our system. That is okay. I mean, there are nice examples actually of linear systems that for which the theories can be successfully applied. But in general, I mean, looking at linear systems only, it's a kind of strong limitation. So one can ask if she can do better. And again, the answer is in the affirmative. And here the idea is essentially to mimic what people do in boundary linear logic or coeffects and similar fields, which essentially means to refine the syntax in such a way to have a tight control on duplication. And what we do in this case is to endow operation symbols with modal arities, which are just a bunch of functions from real numbers to real numbers, which act as the sensitivity or the Lipschitz constant of the function, which in particular tell us how distances should be amplified when performing a reduction. So that we see that if we have a reduction from T to S with error epsilon, and we want to perform that reduction inside the function symbol f, we just look up in its modal arity, okay, what is the sensitivity of f at that position, and we amplify the original distance using that function. In the case of our running example, we can indeed refine our original systems using this idea of modal arities, and what we obtain is essentially an extension of bounded combinatory logic. So now among operation symbols, together with application, we have these new bang operation symbols, which essentially tell us how to amplify distances. And using that operation symbols, we can, of course, reintroduce the W combinator in a controlled way. And we see that using this solution, well, the counterexample to confluence that we had before now is not a problem anymore, because when we reduce the successor of 0 into 0, producing a distance 1, well, then we see that the bang tell us that we have to amplify the distance by 2, so that we obtain a confluence diagram. And that's no coincidence, because the system that we have, I mean, this graded refinement of our original system is indeed confluent. And as for the linear case, this follows from a very general theory in which we have these proof techniques like orthogonality and critical pair lemmas, critical pairs, and so on, that holds in the setting of graded quantitative systems. All right, so these are just a few techniques and a few results that I showed you for the setting of this specific example. But if you look at the paper, there you will find what I like to call some first steps into quantitative rewriting. And as I said, by first steps, I mean that we have a theory of abstract systems and a theory of term-based systems in which we refine many results, but mostly concerned about confluence of traditional rewriting. In particular, in the theory of term-based systems, we study both linear and graded systems. And together with that, we also have some examples and applications, such as quantitative algebraic effects that come from barycentric algebras and similar things, and on string algorithms, for instance. So we show that we can model things like the Hamming and Levenstein distance using quantitative string rewriting systems. And concluding, let me spend just 30 seconds about future work. So as I said, the work is essentially some first steps into quantitative rewriting, and that suggests that there are quite a lot of things to do. In particular, we focus on confluence, and we just have few results about termination. So that's something that should be studied more deeply, and then we should also study strategies, higher-order rewriting, and so on and so forth. So there are many things to do. But one that I would like to mention among those is the study of metric word problems, which essentially means that we have these quantitative equations and we want to find our rewriting strategies to approximate it or even to exactly compute the distance given by that equation. And this is interesting because it gives some connections with other fields like optimization, and dynamic programming, because, well, you can approach many distances like the Kantorovich distances in that way, and giving a solution to the word problem can be viewed as a way to compute such a distances, and maybe you can come up with strategies based on dynamic programming and similar things. So, well,